also give some very brief examples. So maybe I give a concrete example, then you know how this entropy actually is calculated. Right, so suppose now we pick a password. So the password will be picked. Suppose we know that the password will be picked using this particular format. So this is like a 5-character password. So the first password is chosen from the alphabet of all the uppercase letters, English letters. So the second word is chosen from the lowercase letters, all the possible lowercase letters. The third one is a digit. The fourth one is chosen from this set of special characters. And the last one is fixed, is this hex key. Okay, so suppose this is basically, say, the format of the password. So now, based on this format, we can actually determine the entropy, right? So to determine the entropy, basically, we can calculate n. N is the total number of possible passwords, right? So how many possible possibilities for the password? So basically, for the first position, how many possibilities? For all the uppercase letters, how many possibilities?
26.
26. Second one, lowercase letters?
26.
Also 26. Third one, digits?
10.
10. The fourth one, you have 4. You choose from these 4. How many possibilities?
6.
4. So the last one, you fix it, so you only have one choice. So how many possible passwords in total? Here you add them or multiply them?
Multiply.
Multiply. So don't make a mistake. Many students actually make a mistake. They add them together, add these numbers. But you need to multiply these numbers because each position actually, because each position you have so many possibilities. So if you want to count the total, you need to multiply them. So in this case, so this is n. So basically now log n will be the entropy. So log n actually is equal to log 2 base 2, 26 times 26 times 10 times 4 times 1. So actually this is equivalent to a log base 2, 26 plus log base 2, 26 plus log base 2, 10 plus log base 2, 4, and then plus log base 2, 1. Right? So because the logarithm, if you have multiply, you can now add them together. Basically, the entropy of the whole password is the sum of the entropy of each individual character. Right? So you can add the entropy of each individual characters, then you get the sum is actually the entropy of the whole password. So in this case, log base 2 to 26, this is roughly, I think 4 point something, right? Because 2 to the power 4 is 16, 2 to the power 5 is 32. So this is 4 point something, this is 4 point something, this is about 3, this is 2. And in particular, this one is 0. The last one does not carry any entropy because log base 2, 1 is 0. So the last one, because it's fixed, it does not carry any entropy, right? So because entropy is associated with uncertainty, if there is no uncertainty, then it does not carry entropy, right? So this is basically an example to illustrate how to calculate the entropy. You can either calculate the total possible passwords and then you do log base 2, or actually you can calculate one by one and then you add them together. And basically that's the way you can calculate the entropy of a password. Right, so this is one example to illustrate. Suppose, of course, this is based on the assumption that you know actually how this password is generated, right? Okay, so any question? So for this part, you know how to calculate the entropy, right? So you calculate the total number of possibility and then you do log base 2. Okay, so that's for example for this password entropy. So now we will continue. So we will look at the protecting mechanism. So basically the protecting mechanism, so we can have, for different attacks, we can have different mechanism. For password guessing, as I said, you can just count the number of incorrect login, fail login, then you can block the account if you have this threshold. You exceed the number of threshold, the threshold set for the number of fail login. And then another way is to slowly process password. So this actually is done by some password systems. For example, so this is called a password stretching. So if you search on the internet, this is called password stretching. So essentially, instead of immediately tell the answer, we may slowly process this verification process. And one particular way used, one particular mechanism used is the so-called B hash. So if you use MD5 or SHA-1, actually it's not good to store the transform password using MD5 or SHA-1. But if you use another hash function called B-hash, actually this it applies this method. So it basically will process the password slowly, so that for the attacker it will take a longer time to do the password testing. So for the individual user, actually it will not have a significant delay. For example, you just every time you log in, the server give like maybe half-second delay. For individual user, because you just not log into the server normally, you won't detect such a difference. But for the attacker, actually, because attacker need to enumerate all the possible password, and then each time it will have like a half-second delay. You accumulate the delay together, that will significantly delay the overall time for the attacker to find password, because the attacker need to enumerate all the possibilities. So later, actually, when we look at this hash of password, so I will probably give more information about this part. So if you use MD5 or SHA-1, actually that's not good, because there is no such possibility to delay. But if you use something called B-hash, actually it can cause, user can adjust the amount of delay for processing a password. So that's, in general, that's called password stretching. Right, so these are the mechanisms to prevent some particular attacks. Then another mechanism we can improve the security is to improve the quality. For example, by increasing the entropy of the password. Right, so in the previous slide, the cartoon actually demonstrates. So if you have some good mechanism, actually you can have a high entropy. High entropy means you have more possibilities for the password. We cannot control the attacker's testing speed, because it's controlled by the attacker. If the attacker is rich, he could buy a lot of GPUs and he could have very fast processing time. So we could not control the testing time of the attacker, but we can improve the quality. That means we enlarge the number of possible passwords, we increase the entropy. Right, so if we use the example in the previous cartoon, actually we can know, we should know that actually sometimes we can use so-called passphrase. So passphrase actually is an alternative compared with normal single password. So passphrase can be like a combination of a few words, and then now basically you enlarge the number of possibilities by using multiple words. And then sometimes you can also do some modification, because if you simply use passphrase, so maybe if the attacker actually, if you use some common words, then there is still the number of possibility may still be small. But you can do some tricks. You can use some tricks to enlarge the entropy. For example, actually you can insert some characters. For example, you can replace the letter O by 0. Maybe you can replace the letter L by 1, the lowercase l by 1. So you can replace B by 8. So basically now it is possible that for the particular character, it is the original character, or it can be a replaced character. So in this case, So if you have, say, each position now you have 2 more possibilities, then actually you have 2 possibilities instead of 1, then actually you can increase the entropy. So this is some other mechanism we can use to use in conjunction with the passphrase to increase the entropy. Right, so of course, if we use a passphrase, we still can have something similar as a diction attack or like a hybrid attack. So basically, in this case, the attacker, instead of enumerating all the possible passwords, then the attacker may try to enumerate all the possible passphrases. Right, so if we do some like a trick to replace the letters with numbers, then the attacker may also do this kind of replacement in order to test all the possible like passphrases. Okay, so these are the rules usually used by the password systems. For example, you need to have like numerical letters and numerical characters, and also then the uppercase letters, lowercase letters, special characters, and so on. You need to change password like every 3 months and so on. Alright, so you cannot reuse any of the previous 5 passwords and so on. So all these kind of rules now are common for different type of systems. Then suppose we have such kind of rules. So how to generate a high quality password that can satisfy the rule, but at the same time can have a high entropy. So that's basically what we need to consider, right? So if you don't satisfy the rules, if you simply choose, although we can use passphrase to have like high entropy password, but if you don't satisfy the rule, basically the system will reject your password. So then how to create a password that can satisfy the rules, but on the other hand, you can still have the high entropy, then we can actually use some like modified version of the passphrase. For example, so you may pick similar to the previous like passphrase example. You can choose a passphrase, but this passphrase should be difficult to predict. So if you remember in the cartoon, actually we assume each word is randomly chosen. However, in reality, unless you can have some picture in your mind to link this passphrase with the picture. Otherwise, it's difficult to memorize. But in general, actually, you can use some other way, so that allow you to link like the words, and then you can still produce high entropy password. So one example is you can choose a sentence. For example, this is a sentence chosen by you. Alright, and then actually you can just, of course, so if you use this one, it may be too long, but you can choose, for example, the first character of each word, and then you put them together, right? So, and in addition, actually you can also do some changes. For example, you can replace this L by 1, you can replace this B by 8, so you can also do some changes here. So in this case, actually you can produce a password which actually is derived from a passphrase. And then you have basically a strong password which can satisfy the rules, and also at the same time it will have the relatively high entropy. Right, so here if you don't have any digit here, for example, if you don't have any digit here, so you may replace some of the characters 2 digits. But you should avoid choosing some sentence like this, because if we have some common like sayings from famous people, if you choose them, then basically this is not like as good as a random sentence in the second example. So if you choose the second one, it's more robust against the like diction attack. So the passphrase diction attack. For this one, is more vulnerable to the passphrase diction attack. Right. So another important like remark about the password is we need to distinguish the online and offline guessing, the enumeration. For the online enumeration, as I mentioned, we can actually prevent this kind of attack by just restricting the number of failed logins. But for the offline guessing attack, this is more dangerous. So the offline happens when the attacker obtains something related to your password. So this can happen, for example, when the attacker obtains your like a transformed password. Say the attacker has hacked into the system and obtained the so-called password table. So in this case, the attacker does not directly obtain your password, but a converted password. However, this converted password now becomes a basis to compare against. The attacker can do the guessing attack, like the brute force or diction attack, and then basically for each possible password, it can do the transformation and compare with this transformed password. Then, if the attacker identifies a correct match between the two transformed password, then attacker can identify the correct password. So this kind of attack can happen when the attacker obtains the password table, or when you actually do the remote logging. If you do the remote logging, for example, in the 368, probably if you study 368, you know the NTLM. We use a hash of the password. We use a hash of password to do logging. But the hash of password is similar as the password table. We use a transformed password. But if the attacker can obtain this information, then the attacker can compare this hash password against the hash of all the possible passwords in the password table, and then see which one gives the correct match. So in this case, we can do the offline guessing attack. So offline is more dangerous because the user or the server, they are unaware of the attack. Attacker basically obtains some information and then perform this attack offline. You can do the attacker can perform this password guessing attack without the awareness of the user or the server. So this is more dangerous compared with online. Right, so the online, offline, actually the difference is not whether there is internet connection or not. So this, actually I test this question several times. Every time I ask what's the difference between online and offline, so many students will answer online will require internet connection, but offline does not require internet connection. But that's not the key point. The key point is whether the testing is limited or not. For online, that means you are testing against a live system. So the number of testing is limited because if you try several times, you fail several times, then the system will basically lock the account. But offline, you don't have such kind of limitation. So the difference is whether the number of trials performed by the attacker is limited or not. It's not really about whether there is internet connection or not. Okay, so that's the difference between online and offline attack. So if I test this question again, so don't make the same mistake again. So the difference is whether there is restriction on the number of trials that can be attempted by the attacker. Right, so for the attacker, of course, so even if you choose a large, like a high entropy password, then attack, if they have the sufficient resource, actually they can still perform like the password testing fairly quickly. Because nowadays we have a lot of tools, so that can be utilized by the attacker. For example, GPU actually is one particular tool used by the attacker to do the password guessing, because you can test password in parallel, right? So there is no a link between different passwords, so you can just test them in parallel. Right, so now in the previous part, we looked at some general information about the password, then and also some general text. So next part, we will look at how password is stored in the operating system. So we will look at the Unix system as a typical example, and then we will look at the hashing and sorting. So these are the two mechanisms used by Unix. So hash basically is the hashing is done by using a so-called cryptographic hash function. Like I said, we can use MD5, SHA-1, and so on. So, however, if you want to have better security, so you should use something called something similar as like a bhash, because that actually allows the user to adjust the response time. So this basically can delay the attacker by slowly processing the verification of the password. Okay, so what is hashing? Hashing is basically it's different from the hashing you studied in 2-3, the data structure. So this hashing is for security purpose. So we use a so-called cryptographic hash function. So this can produce we call a message digest, or like a thumbprint of the message. So basically the hashing can be done for arbitrary size message, but the output has a fixed size. So no matter how long the input message is, this hashing will produce a fixed size output, fixed length output. Right, so if you have 1 bit input, the size of output is fixed. For example, MD5, it will be a 128 bit, that's a 16 byte. SHA-1 will have a 20 bytes, 160 bit. So if you have 1 bit input, hash output will have for MD5, 16 byte. If you have 1 gigabyte input, the hash output is still 16 byte. So that's basically the general definition of hash. Basically, it will transform data from arbitrary length input to a fixed length output. Right? So we call the output a message digest, or you can say this is a thumbprint of the message. Alright, so there are some requirements. First, hash must be efficiently computed. So this is about the functionality, not the security. So we must quickly produce the output from the input. Right, so this, as I said, this output is referred to as a hash value or message digest. Right, so if we look at some simple hash mechanisms, actually they can satisfy this efficiency or a functionality requirement, but they are not secure hash functions in terms of security. So one example, for example, you can simply do a modular operation. For example, if you have X, so you can transform any binary string. So you can transform any data into binary string. You can convert binary string into an integer. Then one simple way to do the hash is you can mod number, and then you have you use the remainder as the hash value. So another way, you can just take a fixed size, a fixed part of the input. For example, you can take the least 16 bytes, or the least significant 16 bytes, or the most significant 16 bytes as the hash value. So if you don't have the sufficient input, maybe you can just do some random padding, or you can pad a lot of zeros. So in this case, we can still produce fixed size output for arbitrary size input, and then efficiency is still high, but these hash functions are not good for security purpose because they don't satisfy the so-called one-wayness and the collision resistance. So for the hash function, we require high efficiency in computation, but so more importantly, we want to have some security properties. So the two security properties, actually there are more than two. You will study in detail in 361, and in this subject, we mainly look at the two important properties. One is called one-wayness or pre-image resistance. One-wayness, that means the calculation of the hash value is one way. Given the input, you can efficiently calculate output. But given the output, you cannot find the input or the pre-image. So that's the one-way or pre-image resistance. That means you can only do the calculation in one direction, but not the other direction. The other one is collision resistant. That means it's computationally infeasible to find two messages which will produce the same hash output. So collision will definitely exist. So we don't use the term impossible. Collision definitely will exist because imagine, so you have a hash function with a fixed size output. That means the number of possible output is fixed, but it can take arbitrary size input. That means the number of input actually is infinity, right? So you have infinite many inputs, but you have fixed number of outputs. So collision will definitely exist. This is simply the pigeonhole principle, right? So you have a list of pigeonholes, you put the letters, but if you have more letters than the pigeonholes, then definitely you will have two letters, at least two letters in one pigeonhole. So in this case, you have collision. So if the size of the input space is larger than the size of output space, you definitely will have the collision. But we want to make sure it's difficult, very difficult to find collision, although they exist. So that's the collision resistance. So it's computationally infeasible, not impossible. Infeasible to find, very difficult to find two different messages which produce the same hash output. So actually nowadays, like SHA-1, MD5, they are no longer collision resistant because MD5 was broken a long time ago, and the SHA-1 I think broken recently by if you actually Google produced some collisions for the SHA-1, and nowadays we use SHA-256 or SHA-3. SHA-3 is the new standard. SHA-256 is still widely used in, for example, in blockchain. In Bitcoin we use SHA-256. So that's the SHA-2. Usually we call it SHA-2. It's the same as SHA-1, but the size of output is longer. So instead of 160 bit, we have 256 bit. So this picture illustrates the two properties. So first is one-wayness. One-wayness means given the input is easy to compute the output. However, given the output, hash output is difficult to find the input. However, the input may not be unique. So we require that given the output, it's difficult to find any valid input. Because we know for output here, there can exist multiple input, but it's difficult to find any of them, any input that can produce this hash. So given a hash value, it's difficult to find any preimage, not necessarily the one you used to produce the hash. And the collision resistant means it's difficult to find two different ones, which actually will hash to the same hash value. So these are the two requirements. Right, so if you look at the password, if you study these two properties with password, you can easily identify why we need these properties. One-wayness, that means if we hash a password, we store the hash value instead of plain password, then it will ensure even the attacker can obtain the password table, like the hash output of the password. The attacker cannot directly get the password because you only get the transformed password, right? So this is better than storing the plain password. Because if you store the plain password, attacker breaks into the system and then obtain the password table, then attacker directly gets the password. But in this case, if we store the hash of the password, but not the original password, then even the attacker obtains the hash value, attacker cannot get the original password because it's difficult to find the preimage, which is the original password. So what the attacker can do is you create a dictionary, you hash them one by one, and you check which one gives the correct hash value. If you get the correct hash value, that means you locate the correct password. You cannot directly get the password from hash. What you can do is to do the brute force, to check, to hash each possible password and check one by one. So that's related to the one-wayness, right? So one-wayness means even attacker obtain the password table. Attacker does not know your password because it only stores the hash of the password, and you cannot invert the function to find the password. So that's why one-wayness is related to security. Collision resistance is related to another important requirement for password system. What is the requirement? So we want to have a low false positive rate, because if you have collision resistance, that means if you have two passwords, you won't have the same hash value. That means you cannot use the second password to log into the system because you don't have the collision. But if you don't have collision resistance, that means you can easily find two passwords which have the same hash value. Then you can have a false positive. Right? So now basically we store the hash of the password instead of the plain password. So when your user enter a password, the system will hash the user input and compare against the hash value. So we only now store the hash value, right? So not the plain password. So once basically the user, there is a matching between the hash value, the stored hash value, and the hash of the user input. If they match, that means the user has the correct password. If they don't match, that means the user will be rejected. So in this case, So collision resistance will ensure that we don't have the two passwords. We can't find two passwords. If we go to find two passwords, which will have the same hash result, hash value. In this case, we can reduce the false positive rate because you can't have two passwords which will have the same hash value. You can't use a second password, different password to log in because of the same hash value. So these two properties actually can be related to the requirement of security requirements of the password-based system. So one is about the secrecy of the password. You cannot directly reverse the hash to get the password, even the attacker obtain this password table. The second one is to ensure you cannot use the wrong password to log in because you cannot produce collision. So that's the reason we need these two requirements. And the common hash algorithm include like the MD5 SHA-1. So these are the common hash functions. Right. So now back to the password file. So as I said, now we install we store the hash of the password instead of the plain password, right? And the collision resistance will ensure we have low false positive rate. That means you can't find a different password which produces the same hash value because hash is a collision resistant. So this will eliminate the possibility of false positive. On the other hand, even if the attacker has obtained the password table, then the attacker cannot obtain the password because hash is one way, right? So what the attacker can do is to do the brute force. Because hash is public function, so the attacker can do is you just create a dictionary and you hash them one by one and check which one gives the correct hash value. If you find the one that gives the correct hash value, you find the password, right? So that's the only way. So basically, the one-way list will ensure that the only way the attacker can do is like a enumeration or brute force. You cannot find another way to invert the hash function. Right. So in Unix, instead of only using hash, actually we use another technique which is called sorting. But in Windows, actually we only use hash. We don't use sorting. So what is sorting? Sorting is instead of hash the password, we hash password with a sort value. The sort value is a random value chosen by the system. So the user basically will have a user ID and then the hash of password. So now we don't store the plain password, we store the hash of password. And then instead of storing only the hash of password, we store the hash of the password and the sort. Right, so each user will have a different sort value. Right, so you may ask, then what is the purpose of adding this sort? So the sort value is actually stored together with the password table. That means if the attacker can obtain so now basically if a normal user logs in, then the user type in a user password, right? So you type in your user ID and password, and then the system will check, the Unix system will check in the password table to find your user ID. And then it will find the corresponding sort value. Then it will take the input, what you have input as a password, concatenate with the sort value. So this is concatenation. Then you hash these two, and then you compare whether the hash value is the same as the stored hash value. If they are the same, then the user will successfully log in. If they are different, then the user will be rejected. So this is how the Unix system perform user authentication using the hashing and the sorting. So we hash password together with the sort value. So the reason of introducing this sort value actually is to, again, slow down the brute force attack. Suppose the attacker obtained this hash table, right? If we don't have this sort value, we only hash the plain password. Then when the attacker try one password from the dictionary, say the attacker build a dictionary. If the attacker try one password, the attacker hash the password, then the attacker can check against all the users. Because you only have the hash of password, you don't have this part. All the users only store the hash of password. Suppose we don't use sorting, Then the attacker try one password, hash it. It can compare against a list of users. But if you have sorting, then every time if you pick a password, you cannot just use one hash to compare against all the users. You need to do hash one by one because each user have a different sort value. You pick a potential password, you need to concatenate with this sort value to check Alice's password. You need to concatenate with a different value to check against Bob's password, and so on. So if there are n users, you pick one password, you need to hash n times with different sort values to test one by one. But if you don't have the sort value, you pick one hash value, password, you hash it, you can check against all the users. Anyone matching this, anyone with a hash value matching what you tested will basically be compromised. Because now you can use one hash value, one hash, you do one hash to check against all the users. And the second advantage, so that's the first advantage, we can slow down the attacker by using one hash value to check against all the users. The second advantage is now if you have the same password stored by the different users, chosen by different users, you will have different hash values. If you don't have the sort, if the Alice and Bob choose the same password, they will have the same hash value. So if you compromise one of them, you compromise both. So you know, because you know from the hash value that they are the same password, right? So now if you use sorting, you don't have this problem. If Alice and Bob choose the same password, the hash will still be different. From the hash table, you cannot tell whether any two people they choose the same password or not, because each one will have a unique sort value attached with the password to do this hashing. So that's the advantage of using sorting. So the using sort can slow down basically the attack. So in particular, the attacker cannot use one hash value to check against the whole group of users. And also the attacker cannot easily tell whether the two users use the same password or not by simply looking at the hash table. So this actually is the reason of using sorting. Okay, so anyway, so basically, as I mentioned, so if we use collision-resistant hash function, then the false positive is less likely. Although it's not possible, not impossible, but it's very less likely because we have a collision resistant. Okay? Right, so basically the Unix system uses a function called crypt to do the hash. And in Unix there are two crypt functions. So you don't confuse these two functions. So one is the utility function to do the real encryption. So one, if you run the crypt in the Unix terminal, actually you are doing encryption. There is another crypt function, which is the hash function. So don't mix these two. All right, so one is for encryption, one is for the hashing. So we are interested in the second one. The second one is for hashing. All right, so basically if you use like a Unix, the old version of Unix, actually it will produce a hash output which contains 13 characters. So the 13 character actually also includes the sort. The sort actually is in the beginning of the 13 characters, and then you have the hash value. All right, so no matter how long the password is, so basically the hash value, the hash produced by this script, will have 13 characters, right? And if you use the same password for different users, then you still get different hash values because of the sorting. Because every time when we hash password, we can calculate a sort value for a new sort value for users, for new users. So in this case, even if you use the same password, you will get different hash values. Right? So there is some code provided in the sample code. So you can actually run those code to have some experience. So you can run the sample code in the Unix. For example, you can connect to Banshee and run the sample code. Right? So this is one simple example to illustrate how this sorting works. So this is a Perl script. So by the way, in the lecture notes, sometimes you will see some Perl script. But I will explain the purpose of these those Perl script programs. You don't need to worry about the details because this is not required in your assignment or in your exam. So I will just use Perl script as examples to explain some ideas. So here we can use the Perl script to do this sorting and hashing and sorting. For example, so in this case, actually we can create an array of sorts. This is an array of random sorts. So every time when you hash a password, right? So you ask the user to give a hash password. This is from standard input. Then you run this script. This is the Unix hash function. So it will hash the password concatenately with two random strings chosen from this sort array. So you choose one random item from this array, and you concatenate. This dot is concatenation. You concatenate with another random item chosen from this array. Then you hash the password with these two randomly chosen elements from the array. So in this case, this is a simple program to illustrate how this hashing and sorting can be achieved. So if you run this Perl script, so you can get different hash values even if you have the same user password because the sort values are different. Right? So this is even in the sample code. So if you are interested, you can run this code. So in the Unix, actually if you install Perl in your Windows machine, you can also run the Perl. Right? So you can install the active Perl and then you can run it. So this is to illustrate to how this hashing and sorting can be done. And then for the newer version of Unix and Linux, actually we can employ other hash functions like MD5 or SHA-1. Actually they will provide stronger hashing than the crypt. And then you may ask, where is the hash user password table stored? Actually, depending on the version of Unix. So in the old version, it's stored in the so-called password file. So this is the password file. That means it stores the password table. So if you go to this like a directory, and then you can find this password file, and everyone can read the password file, but only the root user can modify the password file. That means only the root user can add new users or delete users. But all the users, other users, they can read the password file. So the password file includes the username, the hash of the user password. Actually, this is a sorted version of the hash, and then some other information. Right? For example, the default shell that will be executed when the user connect to the system. Right, so here are some explanations about the items. So we will study some of them again in access control. For example, the user ID, group ID, and so on, because these will be related to access control. But for now, you just look at the username, password. All right. So later we will look at some other items when we look at access control. And then now in the newer version of Windows, Unix and Linux, actually now basically the password is no longer stored in the password file. We store it in a separate file which is called a shadow file. So the password file now in the newer version of Unix and Linux, we no longer store the hash password. Although we don't change the name, but it no longer contains the hash password. The hash password now is in the so-called shadow file. And then now the shadow file can only be accessed by root user, like an administrator in Windows. Even the reading permission is denied. So for other users, no user can read or access the shadow except the root user. But the password file still can be read by all the users, but can only be modified by the root user. Right, so this will introduce additional level of security because now basically only the root user can see the hash of the password. Other users, they cannot see the hash of the password because if there is some malicious insider, they can log into a system. If they can see the hash of the password of all the users, then they can do the brute force attack to break all the user password. But now, since only the shadow file contains hash of password, and only the root user can access the shadow file. Then this prevents the normal users from obtaining the hash value of the password. So even the hash value is hidden from the normal users, so you cannot do the brute force or dictionary attack in this case. Right, so now basically in the new version you can have a password file, but password file no longer contains the hash password. The hash password is in the shadow file, not in the shadow file. Okay, so basically this is an additional level of security provided by the shadow file. However, so depending on the configuration of the system, sometimes if the system is configured wrongly, the shadow file may still be exposed to attackers. So one example here is in this Solaris system. So this is a very old vulnerability. So actually even the user here, the user tried to log into the local host and then type in a wrong password, but actually in this case basically the user will be denied because the password is wrong, right? However, actually the system dumps the code with the shadow file. So in this case, actually you can identify all the hash password, the hash value of the password from the code dumped by the system. So this is like a configuration problem of the system. And in this case, actually we use a utility function called strings. This is a very useful function. So we will see this function again in this utility function again in the subsequent topics. So the string basically can display all the printable characters in a file, no matter this is like a object file or like a normal file. So even if you have a binary like a code, you have an exe file, the strings, this utility function can still display all the printable strings in the object file. For example, if in your program, so you can look at a simple example. So suppose you have a program like this. You compile this to an exe file or like a binary file. So in this case, basically if you use the strings against the exe or the binary file, you can still see all the strings you hard-coded in the program. If you compile this one in Windows to exe, you use the strings against the exe, you can still find all these strings hard-coded in the program. So essentially, this tells us you should never hard-code your password, because if you hard-code your password, even say you compile the program to an executable file by using some utility function like this, you can still locate the password within the exe file. So this is a simple example to illustrate hard-coding the password is not a good idea. You can use some very basic utility function to locate these strings, including the password. Right, so this is basically the warning for you to when you do the programming. And then sometimes, so you may ask, if I don't hard-code the password, how about I hard-code the hash value of the password? So in this case, the string utility may not be able to locate this password. However, so if the attacker knows where actually you store the hash value, the attacker may replace the hash value by a different one. So this can be done by using some other tool, for example, the hex editor. So if you use a hex editor, you can basically see the memory of some program actually you are running. Even if the program is running, you can see the content of the memory for this program. Then you can replace the hash value by a different one. Say you just hash a random password, you replace the original one with this new random hash. Then you can use the new password you used to create the random hash to log in. So this kind of attack is also possible. So for example, if you use some hex editor to edit some running program. So in this case, you still can break into the system even if you store the hash of the password. Alright, so this actually shows you should never store the secret in a program. Right, so it's dangerous to store secret either in plain text format or transform format. It's always dangerous to put the secret. Of course, if we indeed need to do that, we can use some technique, for example, the obfuscation. So probably I will briefly introduce obfuscation later. So how to, for example, if we indeed have secret, how to hide the secret in the program, we can use the obfuscation to do that. All right. So probably I won't be able to cover this part due to the time constraint. So so the demo table, basically, this is what you will need to do in assignment 1. And this is one practical way to hack the user password. So, but due to the time restriction, probably I will not go through, because this may take some time. I think I may need 20 minutes. I can go through this part in 5 minutes, but to explain what you need to do in assignment 1, probably I need another 20 minutes. So, do you want to do it now, or you want to do it on Monday?
Monday.
Monday, okay. So then in the lecture on Monday, so please come early, because